Okay, ladies and gentlemen, we are here for our second and final go around with Cramer's rule. We're going to do an application, and I found a nice problem. And if you're a civil engineer, a highway designer, I'm sure you've come across the situations where you have occasionally seen damage done to a bridge due to a truck hits a bridge, and this can be avoided because usually there are signs which would say maximum height, so forth and so on. So at any rate, knowing what the equation for the curve, usually a parabola, which defines the arc or the arch of a bridge, is important to know. So if you're a civil planner or a civil engineer, these things are important. Okay, so let's look at an example. The opening of a railway bridge over a roadway is in the shape of a parabola. A surveyor measures the heights of 3 points on the bridge and is shown in the figure. He wants to find an equation of the form y equals x squared plus b plus c, which is, another standard form of the version of the parabola. You want to use this to model the shape of the arch, and I assume maybe a town or a village or a state parkway commission is perhaps paying him to determine what height markers should be on the bridge. So use the surveyed points to set up a system of learned equations for the unknown coefficients A, B, C, and solve the system using Cramer's rule. So here's a little picture, and so you have a railway bridge, and the roadway, of course, doesn't go all the way to the end. The car wouldn't fit under there, so maybe from here to here, and then they would have to have a little sign that says how tall the maximum size of a car or truck passing under, or if this is a waterway here, the maximum size of a boat passing under. Okay. So he takes we have a coordinate system. We have x's and y's, of course. And 10 feet out, measures the height is 25 feet tall, and measures 15 feet out, and the height is 33 3/4 feet. And he measures the height 40 feet out, which is height here is 40 feet. So, and by the way, once you know the equation of the parabola, of the parabolic arc here, you could determine the max height, things of that type. So, okay, so at any rate, this is the problem we're doing. So the idea is we're going to transform these three values into a system of linear equations. In other words, when x is 10, the resulting value is 25. When x is 15, the resulting value is 33 3/4. When x is 40, the resulting value is 40. Okay, so that's the general plan. Okay, and here's what happens. Without loss of generality, since we're looking to find the coefficients A, B, C, now we're used to using X, Y, and Z, but we have to be a little bit mentally flexible here. We're looking for A, B, and C. Okay, so and the equation again, y equals x squared plus bx plus c is equivalent. The bridge problem is equivalent to solving this 3x3 system of equations. And the plan is to use expansion by minors with Cramer's rule. And since these coefficients are 1 here, I think it might be wise to expand along column 3. All right, so what I'm going to do is I'm going to make this a wee bit larger so we can see it better. Okay, expand this out. Let's see if this works. Will this work? I want to get it down to 150%, so okay, so here's the plan. Here's our system of equations, right? This would be the x squared when x is 10. This is the x. 15 squared, 225, and this is your um, x, of course. When x is 40, 40 squared is 1600. So that's where these numbers come from. All right, if you're not sure of that, then let's take a peek back at the other version. We've got x squared. So we're taking x to be 10, x to be 15, x to be 40. So 10 squared is 100, 15 squared 225, and 40 squared is 1600. So that's where these numbers come from. Okay? All right, so here we go. Now, we're used to also seeing d for determinant, which we're still using, d sub x. Well, this is d sub a. We're looking for a, b, and c, not x, y, and z. So again, we have to be a little bit flexible. All right? Okay, so here we go. If we are expanding about column 3, and let's do the denominator first, okay? You get 10, 101, 225, 15 and 1, 1640 and 1. This will be the value of determinant of the coefficients d, and that's going to appear in each of the variables we're looking for. So if we're looking for A, we're looking for B, we're looking for C. This will be on the bottom of each of those. So we can do this once, and then we'll come back and we'll figure out the d sub A, the d sub B, the d sub C. Okay, so this is D, the determinant of the coefficients. D sub A, what we do is we replace the A column by the constants. So these guys here, the second, third columns are the same, but the first column, instead of having the 100, 225, and the 1600, is going to have the 25, 33.75, and the 40. Okay, so this is our setup, and let's go through it step by step. Let's do the bottom first, because this is what we're going to be using in each of them. So, okay, so if we're expanding along column 3, all right, we start with this position here, and that's a 1, of course. So we have a multipliers of 1, 1, and 1, right, because those are the values. And don't forget, upper left-hand corner is plus, so plus, minus, plus, and then they alternate. So this will be plus, minus, plus. And that's why I have a positive 1 here, a negative 1 here, positive 1 there. Okay, so now let's work on our minors. Okay, so this is a 1. I'm deleting the elements along this row and this column. I get 225, 15, and 16, 40, and 40. Okay, now if I'm working on the minor of this element, I delete those, and I get 110, 1640, as you can see. And when I get down here, all right, I'm deleting these elements, and I'm left with 110, 225, and 15. Okay, so then I work those out, and that would take us to the next line. So let's see. When you do a determinant, it's the major diagonal minus the product, the minor diagonal. So 225 times 40 minus 15 times 1600. So I wrote this out. 225 times 40 minus 15 times 1600. And over here, it's 100 times 40 minus 10 times 1600, and that appears here. And the last part of this would be 100 times 15, take away 10 times 225, and that appears here. So let me work these out. Let's see. 40 times 225, I think, is 5,000. Is that 5,000? Let's see. 9,000, I apologize. 9,000. Let me get my calculator. All right, because I just gave the result down in the next line. Okay, so 225 times 40 is 9,000. Okay, and we're taking away 15 times 1600. and that gives us 24,000. So we have 9,000 minus 24,000, and that's how we get the negative 15,000 here. And then we do this one. This is a little bit easier. This is 4,000 minus 16,000, negative 12,000. And this one is 1,500 minus 2,250, which is negative 1,750. So you get minus 15,000 minus a plus, plus 12,000 minus 750. So we get negative 3,750 for the value of determinant D. Okay, let's do the one on top. Now, one on top, let's see, I think we did see where this came from. Okay, so if we're expanding along minors, we go 1, 1, 1, plus, minus, plus, because if we start out upper left-hand corner as a plus, signs alternate, plus, plus, and so they alternate here, so plus, plus, so plus 1, minus 1, plus 1, okay? And so let's see, here, we omit the first row, the last column, you get 33.75, 15, 40, and 40, okay? And if we go down to this element here, we look at the minor, you get 25, 10, 40, and 40, 25, 10, 40, 40, good. Okay, we go down here, we eliminate the third row and the third column, we get 25, 10, 33.75, and 15, okay? And we work these out the same way. And yes, I did type all this out, so you know, here we go. 33.75 times 40 minus 15 times 40. 25 times 40 minus 40 times 40. 25 times 15 minus 33.75. Okay, and then you got to work these out. So you put this in your calculator, order of operations, of course, you get 750. This one you can do mentally. That's 1,000 minus 400 is 600. This one you can probably, well, let's see, 10, 2, 20, all right, fine. All right, so whatever you do, you work this out on your calculator, 37.5. Okay, so you got 750 minus 600 plus 37.5 is 187.5 over the negative 3750 from before, negative 0.05. So that would be the A. So that would be the multiplier of the x squared term. Okay? And here is your computation for B. And I will remind you that in this case, of course, the second column, so that would be the B column, is replaced by the constants 25, 33.75, and 40. And here is expansion by minors. And of course, the denominator is D, the determinant of the coefficients, and that, of course, is the same as we previously did, so that's going to be a negative 3750 again. So let's work on the top one. Just do it quickly now. Expanding along column 3. We begin with this element here, which is a positive, right? Positive, negative, positive, right? That's why we get these values. And if we eliminate the top row and the last column, we get 225, 33.75, 1640, okay? Similarly, we get these other minors. Okay, and then everything works out. I typed it up beautifully for you. I really, a lot of work, ridiculous, but then I figured it's done once, and I never do it again, right? Okay, you work these out, and lo and behold, this becomes negative 45,000, this becomes negative 36,000, and this becomes negative 2250. You have to be very careful about these, okay? You gotta, I mean, you can't slop this down as you're riding in your car. You have to sit down, clean space, big piece of paper, and, you know, do the math. So I'm setting it up for you just to show you that it can be done. And you work this out. So this is negative 45,000, negative times negative is a positive, that's plus 36,000, minus 2250 comes out to negative 11,250. B is your negative 3750, so B is a 3. And last but not least, you do the last one, which is D sub C. In this case, we replace the C column, which used to be 1s, with these values here. And don't forget, that is going to have an effect when we expand by minors, because now the coefficients are going to be 25, plus minus plus now, negative 33.75, and plus 40. So that's going to change some things. Okay, so you have to be a little bit careful again. You can't just automatically go with the 1, negative 1, and 1, which we had up here. Okay, so you just got to be mindful. Okay, and you do all the computations. I wrote everything out so you can follow it along, order of operations, and this becomes negative 15,000. This becomes, we could do this one mentally, 4,000 minus 16,000, negative 12,000. And this becomes 1,500 minus 2,250, which is negative 1,750. And lo and behold, the top is a 0. 0 divided by non-zero quantity, 0. So altogether, here's what we get. Applying the values found. This is A, this is B, this is C. If you're asked for an ordered solution triple, here's how you would write it. A, B, C, alphabetical order. You got the parentheses because it's an ordered triple, and you got the brackets because it's a set. And what this comes down to, equation of the parabolic arch, is this. And since C is a 0, we have no constant term. And this would allow an engineer to know the height at every point, and basically then you can know how wide to make the roadway, because obviously, you know, common sense, if you go back here, you know, nothing very tall is going to fit through here. So you need to know how much offset that and the actual lane so that you don't get a lot of collisions. Okay, so that's an application. And of course, in real life, this is done by computers. And most likely what would happen is a civil engineer would have a series of programs that he or she would use based on the arch, or, you know, if they're designing this, and that's how it would work. And if you've been over the Verrazano Bridge lately, I believe, or even the Tappan Zee, if you're a little bit upstate, there are signs that would indicate how tall a boat passing through could possibly be, that it wouldn't damage the bridge structure. And you might say, well, who cares about that? But don't forget, there are cruise ships, there are tankers that are coming in. Also, there are, you know, government military ships that eventually sometimes come in, and this kind of information is necessary. Now, perhaps this is done by laser and GPS now, but still, it's always good if you're able to do this and plan ahead. Okay, so that's an application problem, and interesting problem, and hopefully give you an idea of some of the things that are actually done in industry and in the world, even in civil engineering. Okay, so I bid you adieu. I'm probably going to do some things on sequences, which probably will not be tested, but you're definitely going to need this in Calc 1, and that would be where you folks would be going. So we'll see how this works out. Okay, so have a good evening. Hope you're doing well.